Hey, this is Mr. Ferguson, chemistry students,
And Mr. Hunter.
and we are doing lesson 11.7, the final lesson in our solutions in acids and bases unit. We're talking about strengths of acids and bases.
And our first objective is describe the difference between a strong and weak acid and base.
And then we're going to identify some specific acids and bases as being either strong or weak.
And then use Ka or Kb to find the concentration of H plus and vice versa.
Okay, let's get started with this.
Alright, so the first definition we want to talk about is that of a strong acid, and that's an acid that undergoes 100% dissociation in water.
So if this is our, and we're using a generic formula, so we have a hydrogen ion paired with some generic anion, but this one's strong. That means when this hits water, 100% of this is going to ionize into the two ions. It's going to be, there isn't going to be no more HA left. It's going to be completely hydrogen ions and whatever anion it's paired with.
Alright, the next is a strong base, and that undergoes 100% dissociation in water.
Okay, and again, you can see that we used the arrow that we always use to show that this reaction completely favors the products again. So when we dissolve this in water, we're going to expect 100% of it to turn into those.
Yep.
Not so for a weak acid, though, is it?
Yeah, now we have weak acids and weak bases, and the definition is basically the same. It's an acid or base that does not completely dissociate in water.
So notice that it looks a lot like the strong acid reaction, except that we have this two-headed arrow there, which indicates that we can do the reaction this way and get these two, but the ions can also go back together and make this. Like this substance can stay dissolved but not ionize.
Yep.
And the same thing for the weak bases. We would expect some of the acid and some of the base when it's a weak one to be in its molecular form, not in its ionic form.
Yeah, and the way we can tell how much of these things actually ionize, there's a term for weak acids called Ka. We saw it last video for the Kw equals Ka times Kb. So for a weak acid, they have a value known as Ka. And for a weak base, they have a value known as Kb.
And I think we're going to do that
later
in this
next
video. Yep. Okay, now the solubility rules will give you a rough guide to strong and weak. If an ion is highly soluble, we're going to expect it to be a strong acid or a strong base. Ones that are slightly soluble or not so soluble are going to tend to be your weaker acids and bases.
Okay. Alright, so listed here are a list of acids and their conjugate bases. We did talk about what a conjugate base was and a conjugate acid. If you notice, the Ka value up at the top here is 10 to the 10th. That's a very large positive number, and that's telling me the acids like Hi and H2SO4 that we know to be strong acids are indeed strong. Just like HBr, HCl, H3O, H3PO4, HNO3. These are
from here up.
Well, even HNO3.
Okay, yeah, even HNO3. Sorry, from here up, these are all strong acids because the Ka value is
larger than
1.
And as you go down, then you see HF is 10 to the minus 3, which means it's a less than 1 number, in which case we classify those as a weak acid because they don't fully dissociate when they hit water. So the general rule of thumb is listed below. As you see, Ka can be used to determine the strength of an acid. If Ka is greater than 1, it is considered strong. If Ka is less than 1, it's considered weak.
Okay, we also have 6 strong base. There's not a huge number of strong bases. They tend to be ones that are paired with an ion from a metal from group 1 or group 2. Yep. And those are going to be your strong bases. Anything else like ammonium, hydroxide, they're going to be weaker bases. They don't completely dissociate.
All right, so we're going to give you two specific examples of a strong and a weak acid or base. A strong acid, we're going to say, is HCl, and when you put that in water, it becomes H plus and Cl minus. Now we want to do a weak acid or base for you. We're going to do acetic acid. Oh, you want to do a strong base first? Let's do sodium hydroxide if you want to do a strong base.
Okay, strong base, NaOH.
Goes to...
That's an H. And that's going to go to sodium ion. and hydroxide ion.
Yeah. So the weak acid we're going to do for you is going to be acetic acid. So that's,
Would you like me to write it organically or
yes, write it organically
All
for
right,
them.
CH3COOH. And this is going to be our two-headed arrow.
That's the very key point to remember, two-headed arrow.
And that's going to make CH3COO minus and H plus.
All right. Now we have a specific example of a weak solution going on, or I should say a weak acid or base in solution. And to calculate the things we want to calculate with acids, we have what's known as a Ka value or a Kb value. And they're exactly the same except for what they stand for. A Ka value comes from an acid. The A stands for acid, the B stands for base. So Ka is going to equal our products, a concentration of our products.
So in general, concentration of products
Divided by
concentration of reactants. And this is called an equilibrium constant. Reactants. And we're going to be doing this a lot in the next unit, but we're kind of introducing it now.
Yeah.
Now, if you have more than one product, you need to multiply them, the products. If you have more than one reactant, you need to multiply them. So for acetic acid, we're going to have concentration of acetate ion, CH3COO minus, multiplied by concentration of hydrogen ion. And we're going to divide that by the concentration of the undissociated CH3COOH. So basically, looking at this, you can see if these are bigger, we're going to have a number greater than 1. If this is larger, in other words, if most of it doesn't dissociate, then we're going to have a value of less than 1. And the weak acids, this is generally the bigger of the two.
Now, also, I'm going to tell you now, there's a few rules we're just leaving out for simplicity's sake, because these can get quite tricky. So our mathematical calculations of these equilibrium constants are going to be very simple steps. Know that next chapter you're going to see these again, but they're going to be a little bit more tricky potentially. All right, let's go look at a sample problem of this. All right, so the first question that we ask on this slide is, what does Ka mean? And as Mr. Ferguson said before, it's the equilibrium constant. It tells us how much of the product will be formed. And how do we use this to be useful is given to us in these next 4 steps. So we're going to use a generic acid, generic weak acid, written out as we've seen before. And in any of these problems, they're going to tell us the Ka value if they want us to solve for the pH or the H+. Now, they could also give us the concentration of H+ and expect us to solve for the Ka. And in this case, the K is going to be 4.0 times 10 to the negative 7.
It's generally given to you without any units on it.
Yes.
Okay.
So for the setting up of the Ka equation, we know that it equals 4.0 times 10 to the negative 7. So it's going to be the concentration of a hydrogen ion times the concentration of the generic anion divided by the undissociated weak acid. And then we're going to do something where we plug in our values for things. And this is where things get a little tricky. We know that we have a starting concentration given to us. We haven't said it yet, but the starting concentration for HA is 0.1. So what we do from that is we know as soon as we put it in, a certain amount of this is dissociated. We determine that as X. There is an X amount of this that is dissociated. All right, so the way we write these out is we write down the initial concentration like we did, and as I said just a little bit ago, that any amount of HA that dissociates turns into H+ and A-. So we term that amount that is dissociated as X. So we get X amount of H+, we get X amount of A-, but we also subtract off
because
X amount from HA.
we don't have 0.1 mole per liter now, we have 0.1 minus X.
Yeah.
So we're gonna make this minus x, and then we substitute everything in.
Yes.
So this is gonna be x
Times X.
times x divided by 0.1 molar minus x.
Now, there's a small trick that a lot of people do. When you have a times 10 to the negative value is greater than 5, a lot of people ignore the x in the denominator to make your life easier.
Because it's such a small
Yes.
number.
And for our class for this year, if you take AP Chem, we're not going to ignore this x unless a very specific example. So we are going to ignore the x on the bottom.
So basically, if this is a negative number greater than 5, we're
We're
going
gonna-
to ignore this x down here, which
Yes.
makes the math a lot simpler.
Yes.
Okay, so we're
It
just
avoids
going
the
to
quadratic
kind of-
equation.
Yeah, we don't end up with a quadratic.
Okay, so now we can solve for x, and we solve that x squared equals 4.0 times 10 to the negative 8th. So therefore x, we take the square root of both sides, x will equal, good square root, x equals 2.0 times 10 to the negative 4th, and that's the concentration we just solved for. Remember, they are brackets.
Moles per liter or molar.
Yes. And lastly, they want us to solve for the pH. So pH is equal to negative log of that number we just got.
2.0 times 10 to the minus 4. So what's that work
Equals out to 3.7 molar. So I know a lot of you who are watching this are like, I have no idea what's going on, but we will practice this.
Since that's x, that's our concentration of
H
the
plus.
hydrogen ion and the whatever the anion is paired with. And then we just took that value right into the pH equation.
Yep.
And again, like Mr. Hunter said, takes a little practice.
Yep.
We'll practice it a lot in class.
But once you get it, it kind of clicks. All right. So the first PVQ question you have tonight is what makes an acid or base weak? And then the second one is to set up the Ka equation for HNO2 when Ka equals 5.6 times 10 to the negative 3.
No, we're not actually asking them to
No,
solve for anything,
we
or
just-
just set it up.
Yep, we just want the generic setup equation using x's and
So
the
you're gonna have
numbers.
to write out the dissociation reaction
Yep.
for that acid.
And then say Ka equals whatever divided by whatever, and then that'll
Okay.
be your answer. Have a good night.